All right, hey everybody. Notice things got ratcheted up a little bit here. Questions 13, 15, 17, and 19. Reason why I wanted to film this video is because perhaps you're struggling to kind of remember some Algebra 1 stuff towards the end of the year. But once you had an equation like this, you notice that this might not be as straightforward as simply isolating x like you're used to, just kind of like step by step. I'll subtract 20 from both. I don't know. Like, yeah, this here. The reason why is because x is being squared, right? That's what makes it harder to solve. What potential solutions for x of what x has got to be here is because it gets squared. Sometimes you end up actually with two solutions. You end up with two solutions on this one here because remember, something being squared, it could be a negative number, and if you square it, it becomes positive. And it could be a positive number when squared to remain positive. So anyways, a negative, something being squared that's positive could have the same result as something being negative squared. Could be positive here. So that's why we have two solutions in this one. So anyways, they're giving you kind of steps. I'm not going to go through what they did in their example. That's for you to read. That's for you to see if you recall how to do this. I might just do the other ones for you as examples so you can get into the flow of things here, because I'd love for you to review some of that Algebra 1 stuff late in the year. I think IXL is a great website here. I might show that in a second. Okay, and here's what I was talking about a second ago. IXL.com, Algebra 1. I love this. Some students shared this with me the other day. This is great for getting caught up on areas where you feel like you need more practice, you want more practice, because you want to get better at math. I mean, it's up to you. You want to get better at this stuff here. But anyways, in Algebra 1, towards here, you want to look for quadratic equations. Okay, quadratic equations here. So got a bunch of ways we can solve a quadratic equation using square roots. There we go. That's one here. Solve a quadratic equation using the zero product property. That's what I want to do today. Do we have factoring in here somewhere? I don't know. But solving a quadratic, I'm sure quadratic formula. There it is. Solving the quadratic equation using the quadratic formula. I get an equation like this. I want to solve for m. Well, hey, I want to use that magic quadratic, the quadratic formula to solve for n or to solve for k or whatever. Look at cycling. You need to learn how to solve all these. Ooh, that's going to be imaginary, the answer there. All right, anyways, hold up a bunch of ways to do it. I don't see factoring on here necessarily, but you can always learn how to factor. Okay, factoring, right? There we go. Factoring. So yeah, there we go. Solving quadratic equation by factoring. That's kind of what they did in this one here, isn't it? Like, they did an example. So anyways, perhaps you should brush up on that. I think that's probably even more important than a lot of the geometry stuff I'm trying to teach you this year. So please come meet with me. I know people have met with me here. Let's do this problem together. If you didn't do super solid on this one, I might check in with you. Might look at this when you turn it in here. But anyways, AP is 6. Okay, BP is 8. So we know the power of that point P is what? 48. 6 times 8 is 48. There we go. CD is the whole thing. The whole darn thing. The whole darn thing. And people are still having trouble with this. The question is, how do we come up with an equation to get us to solve this here? Okay, so we know that the power of the point here, right? We know that this here, we're doing these problems here, okay? So they have it all written down. I'm just going to write out the equation we want to use, okay? So here we're going to use the two chords power theorem, okay? And part of the confusion here is that we only have the entire chord here. How are we going to get those links to the segments of the chord here, you say? Because our power theorem is this. AP times by PB. Look, P's in both of them. We're talking the power of point P. So that's the two ways we have on that line to get to the circle is that distance and that distance. Doesn't look to scale, does it? Doesn't look to scale. This looks smaller than that. But anyways, it's just a generic diagram. Okay, that times by equals CP times by PD. That's another way to get the power of point P, which is consistent. So that's why we can say that they're equal. We don't know PC. We don't know PD. So what do we do? Let's freak out for a second. Well, let's put some things in that we do know. Okay, AP is 6. So I'm going to put that in right there. BP is 8. Okay. CP, do I know it yet? No. PD, do I know it yet? No. But what can I do? They explain you up here. They say write a let statement. Okay, write a let statement to define one of the variables. Well, I don't know what CP is, but one thing I do know is that CP plus PD is equal to, this 16 here, this CD right here. Why do I know that? I don't know. How can I justify that? CP plus PD equals CD. Well, that's just simply part plus part equals whole. That's the segment addition postulate, okay? So I know that And I'm going to replace CD with 16. So I got two things going on. I got my power theorem over here. I got segment addition postulate up here. 16 equals CP plus PD. I know that those two equal, sum together to equal 16, okay? So what they say here is it's called defining a variable. You should have done this in Algebra 1, defining a variable. Absolutely hammer home, defining a variable. Let the amount of money that Carl needs to make B per hour be represented by X, right? Like that here, and then you can work on your equation. So here, what I don't care about, the nice thing about geometry is I don't have these crazy word problems. I can just say, let's let this distance, let CP equal X, okay? Let CP equal X. And then it says then, and then do this thing here. Well, how's that? Like, how can we just logic through that to maybe save some steps here? If the whole thing is 16, and this is X, okay, this is X right here, what's an expression we can write for PD, the remainder, what's left over? Well, I think I gave you the answer away by saying remainder, didn't I? If we let CP equal X right here, X in length, this length here is dependent upon how long CP is, okay? Meaning we have the whole length is CD. If X were 10, what's PD? It would have to be 6 because it's dependent on how long this is in the 16 here. 16 minus 10 is 6. If CP were 8, what would PD have to be? It also have to be 8 because PD is dependent upon how large CP is, okay? If CP were 2, and it's not, right? I mean, this doesn't look to scale at all, but CP were 2, what is PD? Well, PD is dependent upon CP, so if X were 2, then PD would be 14. What do we do? 16 minus X. That's what we did, 16 minus 2. 16 minus 8 before that got us to 8. 16 minus 10 before that got us to 6, okay? So PD is 16 minus X, and we can prove it right here because we have the segment addition postulate up here. CP is X. I'll replace CP with X plus PD equal to 16. I'm going to subtract X from both sides using this subtraction property of equality. That cancels out. PD, there we go. We have an expression written for PD right here, an expression written for CP right here. And what do we notice about the variables in both of them? They're both X. Okay, they're both X. So we have only one variable. That's nice. If you've taken Algebra 1 right now, you know it's nice when you have an equation with one variable in it. Why? Well, we can solve for that variable. We can figure out a numerical value that variable is equal to. And if we're not sure how to solve here, I'm going to hopefully teach you a little bit how to solve an equation like this. Shall we? Shall we do it? Yes, we should do it. Okay, check it out here. Let's do it here. So CP is X. Let CP equal X. So I'm going to put that in right here, okay? I'm going to replace CP with X, okay? And I'm also going to replace PD with 16 minus X, okay? So remember, they're separated by multiplication. When you substitute in algebra, when you put a variable in for something else it represents here, you do so with parentheses around, okay? Because CP here, X, is going to be multiplied to the entirety of PD, and that is the quantity 16 minus X right here, okay? So substitute with parentheses. That's what they did. And that's a great example. That's what you should do too, okay? Next step, they distributed. So they use the distributive property of multiplication over addition. Don't remember that? You got to practice that, okay? So we'll definitely be assumed you know that in Algebra 1. So 6 times 8 is 48, okay? Here I'm going to distribute. X times 16, 16x, okay? Remember parentheses, they multiply. When we see parentheses, we multiply. X times by negative x is negative x squared, okay? X times x is positive x squared, but negative x times positive x is negative. I get 1 positive times 1 negative. So anyways, I get negative x squared, okay? What did they do next? Well, it looks like they actually moved everything to the side where the 20 is here, okay? So this is a tip here, and I don't have much space to write, so I just got to tell you my big tips here. When solving quadratics, okay, we know it's quadratic because of this, right? We have x squared here. Again, that's the hard part of equations like this. When we're solving quadratics, we want to get it equal to 0, equal to 0, equal to 0. Why? In Algebra 1, you should have studied things called the zero product property solving. That's how they solve this one, zero product property. You should have studied something called completing the square. I'm not going to get into that right now. And you should have studied something called the quadratic formula. And the quadratic formula, your equation needs to be equal to 0 in order for that quadratic formula to work. And maybe you proved that in Algebra 1. I know I had a lesson on it. maybe you didn't prove it, but you need to accept it, okay? That if you can get something in this form, look, this is, I don't want to overcomplicate this for you. This is just in a form where it's set equal to 0. I won't say a lot of my fancy algebra language to you here, okay? So set it equal to 0. When you're solving for a quadratic, figure out a way to isolate everything. Everything you see here should be on one side of equals, and then what would be left on the other side is just 0. And then you have either the 0 product property to solve or the quadratic formula to solve this here. Okay, what am I going to do? I'm going to add x squared to both sides. I'm going to move everything over to the left side, okay? Because I had negative x squared there, I might as well make that positive. I'm going to move it over here. I got x squared over here. I got 48. I'll deal with that later. And I'm going to subtract my 16x, use subtraction property equality. Subtract it from the right side, got to subtract it from the left side to keep my equation balanced, okay? That goes away, that goes away, that goes away, that goes away. I have 0 on the right side. Now I have x squared minus 16x plus 48, okay, plus 48. All right, so shortcuts time. All right, you might be wondering, this is where I think a lot of people are probably freaking out. This problem is this here. How do I solve for x? You haven't done that in a while. And distance learning was a little rough, like potentially. I was assigning problems. I was doing lessons. But anyways, yeah, hopefully you can get this one here. You're kind of freaking out. Here, they recommend using something called the 0 product property to solve. If we can write this expression, because this is something called the standard form of quadratics, right? Standard form, we have ax squared plus bx plus c. I'm not going to deal with that right now because I think I could factor this, okay? So this is written out with all of its terms already kind of multiplied out, okay? Polynomials like this, you should have studied this last year, but polynomials like this can be written as a sum, right? In terms of all of their terms added together, or they can be written as a product, right? In terms of multiplication. So here, this is the sum, and here, this is the product. Okay, this is the product. So here, you should know how to go between the two, right? Going between the two, that's a pretty important thing, okay? So going from sum to product's a little bit harder than going from product to sum, because here, all you have to do is multiply things. You'd have to do the FOIL method if you study the FOIL method. You have to use a generic rectangle to multiply. You'd have x squared, and then this would be negative 2x's, and then you'd have negative 10x's, and then you'd have positive 20, so then it would simplify to negative 12x's in the middle term. So anyways, that's easy. It's harder to factor this here, okay? The trick to factoring, when I have an a of 1, it's actually a lot easier to factor. I don't have to show you a generic rectangle and a diamond, which is the way that I teach it in Algebra 1. But anyways, if I have a 1 up here, it's actually pretty simple here. To factor this one, if it's factorable, I don't know if all these are factorable too. Remember, sometimes you get things are not factorable when you're doing your algebra factoring, okay? So I'm going to write it as a product, okay? Remember, x times x is x squared, right? It is x squared, right? X times x. So here, I'm sort of maintaining that x squared here. I need to maintain having negative 16x's and positive 48 1s, okay? How do I get the positive 48 1s that are over here? Well, check it out. Negative 10 times negative 2, well, that's positive 20. I need to get numbers right here. Numbers right here that multiply to 48 and will preserve this negative 16x. So here, negative 10 times by negative 2 is positive 20, and negative 10 minus 2 is negative 12x, okay? So the numbers you're looking for here and here, okay, what do? They should multiply to 48 and add to negative 16. So this is a little puzzle here, right? Little puzzle here. I want you to do the factoring way because I love if you get fast at this here. Of course, in factoring units, you go a lot more slowly. We're not doing a factoring unit right now. We're just trying to see if you can apply some of your algebra here. Multiply to 48 and add to negative 16. Well, if we're multiplying to a positive number here, let's try to narrow things down. We're multiplying to a positive number here. What do we know about our two factors of that positive number? Well, they have to both have the same sign. So they both need to be positive or they both need to be negative. Here, we need our sum to be negative. So what are both of those numbers here? They're going to have to be negative. Two negatives added to each other would still result in a negative sum. Two negatives multiplied to each other would be positive here. Okay, so I know that I'm going to have a negative here and a negative here. So the question is, what are my two numbers? Well, negative 4 times negative 4 is negative 16. Negative 4, sorry, that's wrong here. Negative 8 plus negative 8 is negative 16. Negative 8 times negative 8 is positive 64, so that's not quite right. What else here? 10 and 6, that doesn't work. 12 and 4, It's 12 and 4, okay? So x minus 12 times x minus 4 is it. That's how you factor it here. Look, negative 12x's. Negative 4 times by x is negative 4x's. There we go. Negative 4 times negative 12. You better believe it. That is definitely 48 here, okay? So this is factored. We can get our answers right now. How do I get my answers here? What do they do, actually? Let's notice this here. They're using the zero product property, which I don't have a ton of time to go into. But what do you notice about the signs? This is negative 10, this is positive 10, this is negative 2, positive 2. They just switch. That's it. They just switch. And you're doing geometry after all. What do you know about x? Could x possibly be negative? Could it be negative 12? Could it be negative 4 there? No! Distances, lengths are always positive here, okay? So x here is going to equal positive 12 or positive 4, okay? So this is something called the zero product property, right? If x is 12 right here, what's 12 minus 12? 12 minus 12 is 0. What is the parentheses doing? It's multiplying, right? 12 minus 12 is 0. 0 times by whatever 12 minus 4 is, right? 8. So 0 times 8 equals 0. So really what you're doing is you're solving for your zeros of your polynomial. These are called the zeros of the polynomial, right? You want to set your polynomial equal to 0 because it's easy to solve for zeros using zero product property. Anything times 0 equals 0. That's the key to this, okay? So we got here x equals 12 or 4. That's going to tell us that, hey, CP, let's guess. So we're solving for DP right here. DP could be either 12 or 4. Okay, why? Why could it be either one? Well, DP is 4, CP is 12. What's the power of the point? 48. Okay, that works. If DP is, what did I say last time? 4? Did I say 4 last time? I don't know. I was saying 4 again. DP is 4. What's CP? 12. Okay, we got 48. 12 and 4, 48 as well. Doesn't matter. Okay, you get two answers, two potential answers for this one here. All right, let's keep going, guys. Might as well keep going. Let's keep doing it. AB equals 12. CP equals 9. Good. They need to give you at least some of the parts here so you can figure out the power, okay? CP is 9. DP is 4. Some people just like to wake up in the morning and solve a quadratic equation. I swear to God, I met somebody on the street a few weeks ago who said that when they learned I was a math teacher. I'm just like, I just want to wake up and solve a quadratic equation. That's what I want to do every day. I was like, that's sick. You're a sick person like me. But I love it. All right. Anyways, and then we got AB. AB is 12, okay? All right, there we go. The whole is 12, okay? All right, the parts, well, this is 4 times, so what's my power? My power is 36, okay? So here, let's do it together. Now, I show less work this time here because you should be a pro at this power stuff by now. 9 times 4, that's the power of the point. 12, that's the whole thing. We need to go point to circle times point to circle. I'm going to let AP be X, okay? All right, let's statement for you. Let the length AP, let it be X here. Then what is PB? Okay, second addition postulate. Reminder, AP plus PB equals, well, 12. That's AB, okay, AB. And AB is 12, right? AB is 12 here, okay? Subtract AP from both sides, so subtract X, right? Replace AP with X, subtract X from both sides, and there you have it. PB equals 12 minus X, okay? It's what's left over. It's dependent upon how large AP is going to be. We don't know. We don't know what these here. So we're just coming up with algebraic expressions to help us come up with the answer here, okay? So if AP, we let it equal X, we let PB be 12 minus X, whatever is left over from the total length you have here. Part plus part equals whole. And 12 minus X plus X, right? The negative X and the plus X will cancel out. You'd have 12, right? So second addition postulate fulfilled here, okay? There we go. We have it. Let's go ahead and try to do our math of magic, right? Math of magic here. Power of the point, okay? Point to circle. There's X. Point to circle. Here's 12 minus X right here, okay? Multiply it out. Oh, better believe this is going to be quadratic. This is going to be a nice one. 36. I like that. That's a perfect square right there, okay? 12 times by X. That's 12X. X times by negative X. That's negative X squared. Here we go. What am I going to do? I got to set, if I'm solving a quadratic equation, I got to get the whole thing equal to what? What helps you? What's your friend in this one? We got to use the zero product property at some point or quadratic formula. There's only two I cover in algebra, in geometry. I covered completing the square too in algebra 1. Remember that? Completing the square? Ah, love it. All right, anyways, what do we do? Okay, we got to get the whole thing equal to 0. Got to get your quadratics equal to 0. And then you have these crazy methods to solve them that you learn in high school math. There we go. Subtract 12x from both sides. Subtract 12x from both sides. Boom, that goes away. Boom, that goes away. Boom, that goes away. Boom, that goes away. We get the whole thing equal to 0. Okay, so now I have x squared minus 12x plus 36. Ah, that's a perfect square. I like it. Yes, I like it. It's very good. All right, check it out here. I have this, okay? So I'll just do this. I'm working too far ahead. I got my math teacher brain on here. I just got my math taker brain because I'm not really teaching that here. Let's teach it I'll teach it to you. Here we go. What do we got? X times X. That gives you X squared here. What's going to bring me? So here, I need stuff here. Remember, that multiplies to 36, and it adds to negative 12. Okay, negative 12. Well, that's easy, right? 6 plus 6 is 12, and 6 times 6 is 36, okay? But we want to get to negative 12, so what about that? Well, negative 6 times negative 6. Hey, guys, in these ones here, you're always going to have a negative there because your distances are always positive. Let's explain to you here. Okay, so negative 6, negative 6. There we go, okay? So what is X? Well, I only have one solution here. I actually got something called a double root, right? A double root of this, which is nice here. This is because this is a perfect square. This is X minus 6 squared. Okay, so what does X have to be to make X minus 6 squared 0? Okay, zero product property just needs to be the opposite. 6 minus 6, there's your 0 right there. 6 minus 6 is 0. Times by anything equals 0 here. All right, so I got X equals 6. So that means that BP has to equal 6. X is 6. AB is 12. 12 minus 6, well, this is 6. They're both 6. Okay, so that means I got that one done. BP equals 6. This is great. I love this video stuff here. Normally people just do this for homework. They're like, I forget how to do this. How do I do this? Explain this in class. No, here's a video. We got it here. All right, number 17. PT is tangent to a circle. Find the lengths indicated. I can go faster. Yes, I can. Yes, I can. Yes, I can. PT is 6. Well, that's nice because our power of our point here, that's tangent to the circle, the power is going to be PT squared. Okay, I know that because it's a tangent segment. There's only one way I can get to the circle from this freaking point right here. Oh, I got 2 ways here for secants, okay? But for the tangent segment, there's only one way. Square it, okay? All right, PB is 3. AB, what's that one? They tried to trick you here. That's what they did here. So PT, don't get screwed up on these ones here. This is where I'm going to see most of my mistakes. I know it. Okay, remember, power of a point. Point to circle, and I can square it because it's a tangent segment, okay? Other power, using the secant, is point to circle, which is 3. And then is AB point to circle? I'm talking about this is our key point here, point P. AB. No, that just connects, that's just a chord of the circle. It connects circle to circle. We want point to circle, okay? So just a reminder on this one, don't get sucked in by they're asking for this, okay? We can find that later because of segment addition postulate. We'll get there in a second here, okay? So we got here PB, which is 3, times by AP, which we don't know. That's what we need to solve for first. And later, we can go through the segment addition postulate because PB, which we do know, plus AB, which is what we're looking to find, equals AP. So once we have AP, we know PB is 3, we'd be able to solve for what we're looking for, which is AB. That's how that one works. Try to follow the logic here. I don't really know what to say, but I got to move on because this video is long enough here to begin with. Okay, PT is 6. Let's plug it in. 6 squared equals PB is 3. Lovely, we have that. And AP. So this guy, guys, this one isn't that bad. This one isn't that hard. I think maybe these ones you don't need quadratics. Let's see if I can just get it done here. Okay, 6 times 6 is 36. 3 times by AP. Okay, I got divide both sides by 3. I got 12 equaling AP. So I'm not all done. I need to get AB right there, okay? So what we're going to do is to take this. This isn't my answer yet. We're going to plug it into the segment addition postulate, okay? Remember, part plus part equals whole. That's how we agree to measure these things here. If I know this is 3, then I can add this length here, and it would have to equal this length here, which I know, which is 12 here, okay? So 3 plus what gets us to 12, right? Part plus part equals whole. So 12, you already got the answer, right? It's 9. All right, AB equals 9. You already have the answer too because it was in the back of the book. Hopefully you're watching this. Hopefully you're doing it. See the work. All right, let's do this last one here. Hopefully I can just I'll see if I can bring this down. I already wrote on it. Ugly. All right, I guess I can erase it a little bit here. All right, let's check it out here. It's the last one I'm doing for you guys today. Number 21's hard. Good luck on number 21. But I'm doing 19. That's it here. All right, check it out here. PD is 5. CD. Did you see here? I'm just like marking things up. Here, this is, I'm smart enough here to realize this has nothing to, this has an indirect impact on the power. Power is point to circle times by point to circle. In terms of line PC, it's going to hit the circle twice. Point to circle, the segment's point to circle. That's my power here. So what that is 5 times 12, okay? So 5 times 12 is your power. here, PD, CD, what else do they give you? They give you AB is 11. Okay, so I'm going to concern myself with this tangent segment here. I'm going to do PB times by PA. The same thing here. Ooh, tricky. Okay, so this is a little bit tricky here. I only know this. Okay, I only know AB. Okay, what do? I have an unknown. I can actually create expressions for these unknowns here. I don't know what PB is. Look, I only know AB. I don't know PB yet. I don't know PA in total, but I know part of it here. So this is going to work very similarly here. What I'm going to do first is, well, let's just take this little guy. I'm going to let it be X. Let it fly. Let's see if algebra can help us out in this one here. Let PB equal X, okay? So I can have some algebra in my equation to kind of help me out with this one here. 5 times 12 is 60. Also simplify it a little bit here. PB, we're going to let that be X here. So if we let PB equaling X, what can we write for PA? What do you think? Well, this is X. That's 11. And remember, part plus part equals whole. PA plus P, not PA, PB, B plus BA equals PA, okay? So if I want to write an expression for PA, all I need to do is replace PB with X and replace AB with 11. You following this here? This is the beauty of algebra, helping us out with finding a way we can define that variable in terms of an expression using the same variable, the way that we express the other one that we've defined as a variable earlier here. Okay, so simply X plus 11. Okay, and this is going to be quadratic, so I'm glad I'm doing this with you guys right now. Okay, this is 60. Okay, so we use distributive property of multiplication over addition. I get 60 equaling X times X is X squared. X times 11 is positive 11X. Okay, here I'm going to bring my 60 to this side. Remember, so get it equal to 0. One side equal to 0. There we go. Boom, boom, goes away. I get X squared plus 11X minus 60. Uh-oh, is that factorable? Let's see here. Can I factor this? Well, let's try. Maybe it's not factorable here. Get X, X. Okay, so now here, oh, I got a negative there. Did I do something wrong? Okay, negative, I brought it here. Let's see. I think, actually, you know what? I didn't do anything wrong. You're just going to take the positive answer here. So, anyways, this is negative 60. So we need a negative number. Yeah, we'll get this one. I've already worked it out in my head. Okay, so we need a number that multiplies. Okay, so remember, if my A is 1, that's it here. That's one trick here. You're not always going to be able to factor this quickly. Okay, unless our X squared term only has 1 in front of it, or nothing at all, right? Because that's just 1X squared. Okay, so we got to get things that multiply to negative 60, and add to 11. Okay, that's what's going to go here. So what can we do there? We'll multiply to negative 60, add to 11. Well, if we're multiplying to a negative number, one needs to be positive and one needs to be negative. Okay, remember, a positive times a negative would have a negative product. Okay, so that's what I'm looking for here. So let's do some things here with 30 and 2. How about that? Well, that doesn't get you to 11. That would get you to 28, right? 30 and 2 will get you to 28. 12 and 3. Well, that gets you to 17. So maybe we're going to go smaller now. What about 15 and 4? Yeah, there it is. Positive 15 and negative 4. Okay, 15 minus 4 is positive 11. And here we can solve our answers. Because X has to be positive, we're only going to have one answer here. Okay, so that is going to be involved with this one, solving for this one. Zero product property. What does X have to be a true solution to this? Well, X here, if I can make this whole factor equal to 0, remember 0 times by whatever this is, would make y equal to 0. Find a root of the equation, okay? I'm going to go through this quickly, but this is all algebra 1 stuff here. X equals 4, okay? X equals 4 here. So that means that PD in this one equals 4, okay? And thus concludes my video. You got more questions? Come to office hours. Come hang out with me. Do some math. I clearly love doing this stuff. If you haven't noticed in the videos, I love doing it. Come practice with me. We'll have some good times together, okay? Hopefully this helped out a little bit. Hopefully you feel a little bit more confident with quadratics. I don't know. Putting it out there. I'm hoping it helps. All right. Send me a message if you have any questions. Hopefully you have a wonderful rest of your day. Bye.